All right, so first step. Okay, we're going to practice with these quadratics. The first step we want to do whenever you're looking at a graph of quadratic and trying to pick the information out is identify your intercepts, right? We got one here, here, and here. This one is 0, 8. Yep. This one down here is 2, 0. Yep, and the last one is 4, 0. Okay, there you go. Okay. Now, the vertex is also easy to identify at a value of 3, -1. So we now have some information. We can use this. The gimme in these situations that we've identified the intercepts, might as well record them. Intercepts being 2, 0 and 4, 0. My y-intercept would be 0, 8. Yep. The vertex, yep, we also know what the vertex is, would be 3, -1. Right?
Yeah.
Okay. You have then your 3, and you have your n and your m. Now, the n and the m, whichever one you think is m and m, doesn't really matter. I'll explain why that's the case when we start to look at creating the actual function or the equation, right? Being the parent function or the equation. Again, they're interchangeable as cousins, but they're not directly equal to each other. But I'll use the word function for now. But the reason why is because we plug it in, 2 can go first, 4 can go first because it's negative and it's inside a binomial. It's being multiplied to each other, which means that they're commutative. We'll talk about that in a minute. But for right now, let's get the rest of the information in here. Again, our axis of symmetry would be x equals 3. Okay? Just right here. Okay? Right down the middle. Now, what's great about that is that on the side here, I would make a note of something. Vertex asking for x. I'll do CORD for short for coordinate. Okay, so in terms of the vertex, this is asking for axis symmetry, it's asking for the x coordinate. In terms of the max or min, again, look at vertex asking for the y coordinate. Okay? So that means that if we look at this graph, of course, it's up like a cup, which means it is a minimum. Yep. The value of that minimum being, again, the y coordinate of the vertex, which means y equals -1. Very good. So now, again, as I've stated before, I don't really care if you have the value there. That's not so much as important as identifying if it's max or min. When you get higher in mathematics, it will matter, though, if you know what the value is. But for right now, that is important. Of course, we also know that it opens up like a cup. Positive A. Okay, like a cup. And we know our domain is always what? Yep, negative infinity to positive infinity, or all real numbers. The crazy looking R. Right? Good stuff. So the only thing we have left to identify now is the range. Now the range, I would make a note of this below it. Okay. The y value of the vertex included to whatever infinite direction based on max or min. That's what that basically means when it asks for the range. Now, in regards to that range, you have then the y value all the way to positive infinity. Or, if you want to write in terms of inequality, y is greater than or equal to -1. Now, one way to help you guys out with domain and range and understanding what's going on is think of the axes as number lines, okay? For x, if I plug in any number on this number line, it will exist on the graph corresponding to its y equivalent value, meaning if I come down to 6, if I plug in, or if I basically pick 6 and I go up until I hit my quadratic, there's that point right there. Okay, so on the number line. If I go over 1 and I go up, there's my point right there. Any x value is fair game. Granted, we can't do anything in the upper negatives or the upper positives because we can't see it, but it exists because it continues indefinitely up and to the right and up and to the left. Okay? Now, the other thing to consider now in terms of range is this. Range, same principle applies for y. I could plug in any y I want so far. Yep, good, because it's on the line. A good way to test this is that you can use, remember the old vertical line test? Well, we can use a similar thing. Put up against 10. I've got a point here and here. Yep. Here and here. Yep. Yep. 8. In fact, it's right there. It's actually symmetrical. We got a point here and here. A point here and here. Granted, they're decimals, but decimals are still real numbers. They are fine. Okay? I can keep going and going and going. And then all of a sudden, I'm not on the line anymore. That's not good. So that means I can't go past -1. Hence where this inequality, hence where this comes from, and why that's y equals -1. Okay, so that's what range and domain are doing. It's basically setting parameters for values that are allowed in the function. Speaking of the function, let's derive it. Okay, now remember the parent function, which is what we covered yesterday, was y equals a x minus m x minus n. If you would like to write this in terms of f of x, you can. I'm not stopping you. It's perfectly fine. But I write it in terms of y because we're plugging in y's to solve. Okay? So we're going to plug in our intercept and our intercepts, both of our intercepts basically, into this function. M and n are going to go in here. If you put m here and n here, it's fine. It's not going to change your final answer. Okay? So you have 8 equals a times 0 minus 2 and 0 minus 4. So that means that 8 equals a times -2 times -4, which means that 8 equals 8a. All right, so we got 8, a equals 8. So let's bring that over here and up here to finish it. So then we have 8 equals 8a. We're going to divide both sides by 8. 8's cancel. So, yep, a equals 1, which means my equation for this guy will be y equals 1, x minus 2, x minus 4. And there is my equation. Okay. So, that is how you would go about solving based on given a graph in terms of a bit more of an in-depth explanation versus my other videos so far. All right?